Hi everyone. So today is the fourth lecture of our uh, linear algebra tutorial under Dilip Patil. So we start with our first question, that is uh, so we'll so this is a true or false question. True or false? The vectors v1 130 and v2 111 of R3 generate the subspace U A comma B comma 0 such that AB belongs to uh, AB belongs to R uh, of the R vector space R3. So you have to find if the statement is true or false. You can try for 2 minutes, then we'll start. Hello? So okay, let us see that so this is pretty trivial one. The vector v2 111 has a non-zero third component therefore v2 does not belong to U. So span of v1 comma v2 does not belong to U, because if v2 does not belong to U and since U is a subspace, so its span also is not contained in U, therefore it is a false statement. Okay, so now let us go to second statement. For small n belongs to capital N, let Pn defined as 0 union f of kx, where f is a polynomial with variable x over k such that degree of fx is less than equals to n. Then the k vector space P3 is generated by a comma x comma bx square plus x and x square plus x square, where a and b are from k, and also you can assume both of them are non-zero. So you have to find it is true or false. You can try it for again 2-3 minutes, then you can start. Okay, so let us start solving this problem. the dimension of P3 is 4. The given set contains exactly 4 polynomials. So it is sufficient to show that they are linearly independent, because you know that basis is a maximal linearly independent set, and since the cardinality would be same as the dimension of the subspace or vector space, therefore it will be a basis. So suppose C1 of A plus C2 of X plus C3 of Bx square plus 1 plus C4 of x square plus x cube equals to 0. So now if you rearrange it, you will get C4 of x cube, then C3b plus C4 of x square, then C2 of x plus C1a plus C3 equals to 0. So since x cube, x square, x and 1 are linearly independent over field, so this gives C4 equals to 0, C3b plus C4 equals to 0, C2 equals to 0, and C1a plus C3 equals to 0. Now C4 equals to 0 you have, right? So this would imply that C3b equals to 0, and this would imply C3 equals to 0 as b not equals to 0, and you already have C2 0, so nothing to show. And from the last equation, that is C1a plus C3 equals to 0, since C3 equals to 0 you already have shown, this would imply C1a equals to 0, and again this would imply C1 equals to 0 as a not equals to 0. So we are done. So they are linearly independent and therefore it is a basis. Now let's move on to our third problem that says let Pn be above, that is again the set of all degree less than equals to n polynomials, and a of k be fixed. If the polynomials f1x to f dx generate plane then there exists I with 1 less than equals to I less than equals to D such that fi of A not equals to 0. Okay, so again you should try this for 3 minutes, then we should start. It is also a true false question.
Sir, in the last question, can you explain the last part?
Acha, here
Yes, sir. After, like, until that last implies sign, I understood, sir.
like A not equals to 0 you understood?
Yes, yes.
Okay, so what you shown we have shown is that so all okay, yeah, all C1 C2 C3 C4 are 0 if
Yes,
uh, if this equation is 0, then all C1 C2 C3 and C4 are 0. Therefore what we you can say is that a x b x square plus 1 and x square plus x cube are linearly independent, right?
yes,
Then what we have previously talked about that since the linearly independent set has cardinality 4, that is there are 4 linearly independent elements and the dimension of P3 is 4.
Mhm.
Therefore what can say is that it is a maximal linearly independent set, right?
yes.
So there and it is equivalent to a basis, that a basis is a maximal linearly independent set.
Okay.
Yeah, also
Thank you.
minimal spanning set. So there are there should be an exercise or a theorem, you can find it in the book, that if a subset is a basis, then it is
Yes.
linearly independent. Equivalently it is then it is maximal linearly independent set, and equivalently it is minimal spanning set. All right.
Okay.
Okay.
Sir, I have a small question that the when will the assignments be checked, sir?
Okay, so already assignment 1 and 2 are checked. I think you will get the results by uh, Thursday.
Okay.
So
And sir, a little question, sir. I was doing this course, and also I thought of seeing that course on linear algebra by Gilbert Strang.
oh, Gilbert Strang, yeah.
Yes, but the material taught there in the first, let's say, 4 5 lectures is very different from here, sir.
Yeah, so this is more of like abstract, like Professor Dilip, he mainly focused on the mathematical part, like how to, uh, like the things you learn from a book usually. But in Gilbert
Oh,
Strang, it is more geometric and pictorial and matrix oriented, you can say.
okay,
Like both are two different, like semi different approach to learn linear algebra, but you can follow them both, like it will help you later.
okay.
Yeah,
Thank you, sir.
yeah, also yeah, I think there is a book from Gilbert Strang.
Yes, sir.
So
Intro to linear algebra.
yeah, so since you are watching the lectures of him, you can read that book also.
Okay, sir.
Yeah, okay. So yeah, you should try this one, that Pn be above and A is fixed. So if the polynomials generate Pn, then there exists I such that Phi-A is non-zero. So you have to uh, tell me if it is true or false. Okay. Uh, so uh, let us start with the contradiction, that suppose for contradiction that Fi of A is 0 for all 1 of I of D. Now, since the polynomials generate Pn, any polynomial capital Px of Pn can be written as Px equals to I equals to 1 of D Ci Fi of x. Now, evaluating at A, we would get P of A equals to C of I as f of I x, right? Sorry, f of I A. But you already assume that Fi A equals to 0 for all I, so therefore the sum will be 0 too. But what we are claiming is that for every n and for every polynomial from Pn, Pa is 0, right? But the constant polynomial Px equals to 1 is contained in Pn, right? Yeah, and has P of A equals to 1, which is not equals to 0, which is a direct contradiction to our assumption that this Fi A is 0. Therefore, the claim is false. Now, we come to our fourth question, that says let k to the power I denote the vector space of all maps from I to K. Now for small I belongs to capital I, let chi I, the map from I to K, be defined by I going to 1 and j going to 0 for j not equals to I. Then what can we say about this? That then chi I, where I belongs to I, is a basis of k to the power I. So again, this is a true or false question. We can try this for 3 minutes, then we shall try. So you can assume that I is infinite. So there are two cases. We can also take I to be finite also. It would be interesting to discuss both. Okay. Uh, it will be better if some of you try and since you are attending, if you cannot, that is also fine. Okay. So first, suppose I is finite. Then say you can write 1 and I n. You see. Then what happens? Then like suppose f is your function from k to the power I, that is f belongs to I to k, then you can simply write f as write as f of I1, sorry, you can write it as f of ij, ij, and chi of ij, where j is from 1 to n, right? Does this make sense? Because simply if you take f of ik, then it would be j1 to n f of ij chi of ij chi of ik. So for j equals to k, you would get 1, like chi of ij. So chi of ij of ik would be 1 for j equals to k, and would be 0 for j not equals to k, right? Therefore, what would happen is that you only would get f of ik. So one thing is clear, that when I is finite, chi of ij, where your j 1 to n spans k to the power I. Now we have to show that they are linearly independent. So you can take a to ai, sorry, aj chi of ij, where j equals to 1 to n equals to 0. Now if you simply take I of, that is aj of chi of ij of I1, say 1 to n, this is 0, right? And chi of I1 of I1 should be 1, and chi of ij of I1 should be 0 for j not equals to 1. This would give you a1 equals to 0. So for every j aj would be 0. If you take j equals to 2, j equals to 3, j equals to 4, j equals to up to n, so this would imply chi of ij is linearly independent. So chi of ij is a basis. So I think it would be good if you consider the infinite case yourselves. So only trick is there, that if chi I is your basis here, then any function can be written as finite sum of the basis elements. But if you write it as finite sum the function, then you would see that leaving finite values, the function should be always 0. But if you take the constant function, that would contradict the case. So therefore, for I finite, the statement is true, whereas for the I infinite, the statement is false. So yeah, uh, if you have any doubt, you can ask me right now, or else we can move on to our next problem. All right. Okay. Next, move to our next problem. Let f and g are from kx, uh, be linearly independent over k. Then f g are linearly independent if and only if both f and g are non-constant polynomials. Okay. So yeah, again you should try this for 3 minutes, then we shall start discussion. Okay, so let's try doing this. So the question was, if fg be linearly independent over k, then f g and f comma g comma fg are linearly independent if and only if both f and g are non-constant polynomials. So let's check if it is true or false. If f and g are both constant, say f equals to c not equals to 0, then fg equals to cg, right? So 1 of fg minus c of g would be 0. That would imply that they are linearly independent, right? Linearly dependent. Now suppose both are non-constant. So degree of f is greater than equals to 1 and degree of g is greater than equals to 1. Now let c1 of f, c2 of g and c3 of fg equals to 0. Now if c3 not equals to 0, then fg equals to minus c1 by c3 of f minus c2 by c3 of g. Now the degree of the LHS is degree of f plus degree of g, which is greater than of max of degree of f comma degree of g. But minus c1 by c3 of f minus c2 by c3 of f has degree at most degree f or degree g, right? So therefore on this equation the degree of both the polynomials mismatch, yet we claim they are same, therefore a contradiction. Hence C3 is 0, and since F1 and F2 F1 F and G, since F and G are independent, we have C1 equals to 0 and C2 equals to 0, and which would imply C1 equals to C2 equals to C3 equals to 0, and so we are done. Now let's move on to our next problem, that is, let v equals to x square plus x plus 1 fx, to where fx belongs to P3. Then we have to show that, then find the dimension of V. Sir, did you read about the linear transformation and this kind of things? Actually, there is some problem with this question. I think it is written wrong, because V cannot be a subspace since 1 is not there. The question is given wrong in the. Okay, this one is interesting. Sixth one. Find the coordinates of a comma v of R2 with respect to the basis E1 minus E2 and with respect to E2 comma E1 plus E2. Yeah, where again where E1 is 1 comma 0 and E2 is 0 comma 1. Okay, so okay, we shall attempt this. Okay, so you can write a comma b as a of 1 comma 0 plus b of 0 comma 1, right? That is a of e1 plus b of e2. Now for the first basis b1, which is v1 equals to e1 and v2 equals to e1 minus e2, we have e2 equals to v1 minus v2. Now substituting a comma b with a of v1, like putting v1 in place of e1, and b of, since e2 is v1 minus v2, so v1 minus v2, you can write it as a plus b of v1 minus b of v2, right? Therefore the coordinates are a plus b comma minus b. Now for the second basis, b2 equals to e2 and w2 equals to e1 plus e2, then we have e1 equals to w2 minus w1, and substituting we have a comma b equals to a of w2 minus w1 plus b of w1 equals to b minus a of w1 plus a of w2. So the coordinates are b minus a comma a. So yeah, our sum is done. Okay, so yeah, let us move on to our next problem, that is okay, problem let x1 comma up to xn comma x be elements of a vector space, sorry, vector space over a field K. Assume x1 up to xn are linearly independent. Then the first question you should try is that the family x1 up to xn and x1 plus to xn is linearly dependent. But every n of these vectors are linearly independent. Okay, should try this and we will talk about this after 5 minutes. Okay, so you can start solving this. Let S be x1 plus up to xn. Uh, First, let us show that uh, this set is linearly dependent. So let a1 plus x1 plus up to an plus xn plus a of s equals to 0. But you can see that you can take ai equals to I and a equals to -1, and you would see that satisfy the equation. So this set has a linear combination where the coefficients are non-zero. So therefore x1 up to xn dash is linearly dependent. Now to show any subset of n vectors is independent, suppose we remove xi, then the remaining vectors are x1 to xi minus 1 to xn. Yes. Now consider the linear combination equal to 0, that is Cj of xj j not equals to I plus C of s is 0. So this would give us summation Cj plus C of xj j not equals to I plus Cxi equals to 0. Now C1 x1 to xn, you assumed it as linearly independent, right? So Cj plus C equals to 0 for all j not equals to I and C equals to 0, but this would imply Cj equals to 0 for all j not equals to I. So this xj comma s j not equals to I is linearly independent, right? Okay, so the second question is, show that x1 up to xn and x are linearly independent if and only if x1 up to xn are linearly independent and x does not belongs to span of x1 up to xn. So again you should try this for 5 minutes, then we can discuss. Okay, so let us start solving this. If x1 up to xn of x is independent, any subset including x1 up to xn uh, is independent. Now, if x1 belongs to span of x1 up to xn, then x should be some linear combination of xi, right? So this would imply x minus ci of xi to 1 to n would be 0, giving a non-trivial combination of x1 up to xn of x, right? Which is a contradiction, since you have taken x1 up to xn of and x is linearly independent. So x does not belong to span of x1 up to xn, right? Now for the converse direction, suppose x1 comma up to xn are independent and x does not belongs to span of x1 up to xn. Let c1 xi plus cx equals to 0. Now if c not equals to 0, then x equals to summation of minus ci of c xi, meaning x belongs to span of x1 up to xn. Now let summation ci xi plus cx equals to 0. If c not equals to 0, then x equals to summation minus ci by c of xi, meaning x belongs to span of x1 up to xn, contradicting our hypothesis, right? Hence c equals to 0. So the equation that is ci xi equals to 0 implies ci equals to 0 as xi are linearly independent. Thus, since all the coefficients are 0, x1 up to xn and of x is independent, now okay, so let's move on to our next problem. Show that x1 to xn is a generating system of V if and only if x1 xn of x is a generating system of V and x belongs to span of x1 to xn. So again you can try this. It will probably be your last problem today. Okay, so let us start solving this. So if x1 up to xn generates v, adding x to the set trivially keeps it a generating system, right? There is nothing to think about it here. Furthermore, since they generate V and small x belongs to capital V, it is immediate that small x belongs to span of x1 up to xn. Now, for the converse direction, if x1 xn x generates v, any small v of capital V can be written as small v to cixi plus cx. Now since small x belongs to span of x1 up to xn, we can write small x equals to summation aixi substituting this into the expression for V gives V equals to summation cixi plus C of summation aixi equals to Ci of A aic xi. Thus, any small v of capital V can be written using only small x1 up to small xn, showing they form a generating system. Okay, so this will be all for today. We'll meet again in the next class. Thank you.